textbook review. So today we're looking at optimizer. Now, essentially, what is the importance of the optimizer? The optimizer is used to tune the weight based on the training set. All we're learning in our machine learning, deep learning training is a set of weights. The weights are just numbers, and we need to keep adjusting these numbers to what you call the optimum set of weights, to the optimum values that actually represent that solves the problem that we're trying to solve. Okay, so we use the optimizer to tune the weight based on our training data set. We are learning from data set, we are learning from history, we are learning the pattern in the historical data set of a particular problem. So the available optimizers are stochastic gradient descent, the ADA-GRAD, which is adaptive gradient, and ADAM. Then we have the FTRL optimizer. So the stochastic gradient descent is the most basic one. Then we have the ADA-GRAD, which allows for faster convergence, just an improvement on SGD. Then we have the FTRL. I'm just learning this as well. It works extremely on sparse data set that has many categorical features. So if you have a choice, the best is Adam. That is the recommended that you start with. You're free to try other ones. So now, so essentially what's happening is gradient, it's like differentiation in mathematics. So we feed in a batch of data into our network, we calculate the error, we still look at the loss function based on an equation, a loss function between our target and the output of our network. And we calculate the gradient, which is a differentiation or how much the weight contributed to the error. Then the optimizer update the weight with this information. So once you calculate the gradient, we want to go in the opposite direction of the gradient, which we see. Then we use the optimizer to move in that direction. So that is that. So let's look at the gradient descent. Now, when you're training a neural network, so what we're using is we're using the training images and the labels to adjust the weight, like I said, and to minimize a loss function. It's also referred to as an objective function. So, and one of which could be the cross entropy loss. There are different kind of losses. You could optimize the mean square error loss, L1 loss or L2 loss, or KL divergence loss. There are all kinds of loss suitable for different tasks. So the loss function is a function of the model's weight and biases, and the input, of course, which is in our own case is the pixels of the training images, as well as the ground truth, which is the label. So we compute the extent to which the loss changes when we adjust each of the weight, and we get a partial derivative, and of course mathematically the gradient takes us in the direction of increased loss. So since we want to minimize the loss, we move in the opposite direction. So we do the same again for every batch of the training, and eventually it will converge to a minimum. The minimum might not be unique and it might not be a global minimum. So what we're saying is global minimum here is if the minimum that we can have is 0.02, that's the minimum error. The gradient descent might actually, the optimizer might not take us to that 0.02. It might take us to maybe 0.04. So even though 0.02 is the global minimum, 0.04 is still close to that. So and may not be guaranteed to be unique. So what you do is that you can't just update the weight and biases by the whole length of the gradient at every iteration. That will cause the loss to jump from one side of the body to another. So you want to take a smaller step. You just assume, as is depicted in this image, that you are in a rocky area where there are hills, there's mountains, and you want to go down the hills. There are multiple hills. This is a peak of the hill, peak of the hills, peak of the hill. Initially, when you start training, you can find yourself in anywhere. This is what you call the space. So you could find yourself in any of this landscape, any point. So assuming you find yourself here, visually you see that the valley is here and here and here. So those are what we refer to as the minimum. The global minimum is actually this. So you have some other minimum, local minimum. So if you need to now go from here down to this place or to this place, and it's reasonable that you go step by step. If you just take a step from here and you just take a step, you might go into this, and you take another step, you might keep going, and you might never be able to get here, because it requires a smaller step to be able to go in the direction of this minimum, global minimum. So that's what this is saying there. So you need to do smaller steps, and for you to do that, we impose another parameter which is called the learning rate. So the learning rate is how much steps you need to take to be able to get to your minimum. So if you have a batch of images, say 128 images, and it's recommended that you use a batch, because the batch gives you a gradient that better represents the constraint imposed by the different example images, and that is likely to converge towards the solution faster. What does that mean? So if you give like a batch, that means in your feed forward network, in your training, the first batch is like 128 samples. So your network is going to fit all the 128, trying to learn what is common to all those 128 images, rather than just learning what is common to just one image. So that gives a better convergence to the global minimum. So this technique is referred to as the stochastic gradient descent, and it benefits from, you can benefit using a batch where you have 128 images, and that's, you have like 128 matrices, and you can do the matrix operation on 128 matrices on a GPU, because it's optimized for that operation, or on a TPU faster. So that's it for now. So next time we'll look at the training loss. Thank you, and see you in the next one.